Good afternoon, everyone. I'm going to give you a little scenario. Let's say that this is you. Um, and you're sitting here, you know, watching this video perhaps, or maybe you're outside, not sure. But, anyways, you're chilling. And the thought comes to you, um, you know, how heavy is the air? But you're not done with the thought. So, how heavy is the air? Even though there's not enough room in your little bubble here. How heavy is the air over my head? Well, interesting question because there's a lot of air above your head. There's some air right here, right? And then there's some air here and some air up here. And as you go up, it gets a little bit thinner as you get higher, and it heads up for a while. And there's all this air right here, right? Air. Sweet. Air. So down here, we've got dense air. Up here, we have what we might call thin air, Into Thin Air. Great book if you haven't read it, I think. And so it gets thinner and thinner as you go up. There's no real end to the atmosphere. I mean, I suppose at a certain point you might say, well, the atmosphere is over, but there's no like end. So really what you have is a whole column of air above your head with infinite height and decreasing density. So if you wanted to figure out how much that weighed, it'd be an interesting question because you'd be summing up the air from, say, let's say you're 5 foot and 5.4 feet tall or something. And then you'd be summing up all this air from 5.4 to infinity. And you'd have, maybe your density of air times, I don't know, what is density? Density times like surface area maybe, times the thickness or whatever, and you'd have this whole weight here or whatever. Maybe this is just the mass. I suppose this is probably just the mass of the air. And basically what I'm getting at is this is a new situation for us. We have something that we want to sum up, but to an infinite bound. So this would be a scenario where we might want to use what we call an improper integral. Now, improper integrals just work like normal integrals, only they involve a limit. So you're going to have to do your integration normally, but this time you're going to have to use a limit. Okay, so let's look at an example of this. Let's take, for example, the integral from 1 to infinity of 1 over x squared dx. Okay? And really your question here, if we're going back to the mass of the air above your head, your real question is, is excuse me, is this air mass infinite or not? So it's like, well, is there just infinite mass of air above my head? Or does it get thin enough, fast enough, so that even though I'm summing it up to a theoretical infinite height, it will have a finite mass? So that is really the question we're asking with these integrals is it finite or infinite, or does it do some other funky business? And we use the language converge, which means it will reach some number, or diverge, which means that it will head off towards infinity or do some funky business. So this is what we're wondering. Now, geometrically, it'd be nice to think about this. 1 over x squared, it looks something like this, right? And from 1 to infinity as x values, we're curious about this area. So this area is it finite or infinite? So if it's finite, then this had better get close to the axis very quickly because we're going all the way to infinity. Thinking back to the air example, that air had better not be very dense pretty quickly. If it is infinite, then that would mean this is not getting to the axis close enough, and we're just adding up a bunch of infinite area. So basically, to find this, what we're going to do is we're going to replace infinity with a letter and take the limit. So we are going to rewrite this as the limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. So all I have done is replace the infinity with b, and now I'm taking the limit as b approaches infinity, because I can't just plug infinity in. I need to approach it because it's a number. It's not a number, it's just an idea. Now I'm going to compute this integral normally. So I need to know some rules of integration or anti-differentiation. I could rewrite this as the integral from 1 to b of x to the negative 2 dx. And I can just apply the power rule of anti-differentiation to that and have the limit as b approaches infinity of x to the negative 1 divided by negative 1 evaluated between 1 and b. Remember that you add 1 to the exponent. Negative 2 plus 1 is negative 1, and then you divide by that new exponent. So that becomes now the limit as b approaches infinity of, so this is negative 1 over x. So I'll just write negative 1 over x evaluated between 1 and b, which is the limit as b approaches infinity of, now I'm plugging in b and 1, negative 1 over b plus 1. Okay, so I've done all the integration now with b, and now I'm going to take the limit. So as b approaches infinity, negative 1 over b approaches 0. So this limit equals 1. So I have just shown that the area under 1 over x squared from 1 to infinity is 1. And so we would say this integral converges. And furthermore, it converges to 1. That area is equal to 1. So that is kind of crazy, but true. Great. Let's look at another example. Gone. Suppose we had this example. We've got the integral from 1 to infinity of 1 over the square root of x dx. Now that looks very similar to our previous one, but curious minds might be thinking, well, 1 over square root x looks something like this, but it doesn't get as close as quickly, as fast. So perhaps this area will turn out to be infinite because it doesn't get down close to the x-axis as fast as 1 over x squared, which is what we just looked at. But again, all we're going to do is rewrite this with a b and a limit, and take the limit as b approaches infinity. And that would be the integral from 1 to b. I've just replaced infinity with b, and I'm taking the limit as b approaches infinity. And this is x to the negative 1/2 dx. From there, I can simply find the integral using the power rule of integration. And I can get a limit as b approaches infinity of x to the 1/2 divided by 1/2 evaluated between 1 and b. That's the antiderivative of x to the negative 1/2. That is the same as the limit as b approaches infinity of 2 square root x from 1 to b. Simplifying x to the 1/2 over 1/2 to 2 root x. Plugging in b and 1, I get the limit as b approaches infinity of 2 root b minus 2. Well, as b approaches infinity, so does the square root of b. So unfortunately, this tends towards infinity. Which means the integral diverges, and specifically it diverges to infinity. So these are sort of the first type of improper integrals, where basically what you have is you have an upper or lower limit that is infinite. So the type of problems that we just looked at, the first two, are where you have infinite limits. And so what happens is your x value is approaching infinity. So in the next video, we will look a little bit at a different kind of improper integrals, where instead of having infinite limits, you have infinite integrands. That is, the function itself is infinite.